we sent the two Mars rovers, Opportunity and Spirit, to Mars, successfully landed them in a very thin area target using only Newton's equations. Okay, we did not need Einstein's equations, but we have a global positioning system which is based on satellite technology, and you can go to towards the last third of the book in Stephen Hawking's A Brief History of Time, and you will find a reference to the global positioning system using Einstein's equations, theories of general relativity, which were determined in 1915, 10 years after his special relativity. He says that without Einstein's equations, you would be a mile off, and your car would be a mile off when you use your global positioning system to navigate on Earth, if it wasn't for Einstein's general theory of relativity. So we don't need Newton for everything. Well, we don't need Einstein for all practical purposes for many things on Earth. But when it comes to very large, fast things, and when it comes to very small things, such as the implications of E equals mc squared are humongous. It was because of E equals mc squared. Someone's familiar with this next experiment here. Would you like to comment on it? Okay. Actually, this fellow, I'm going to ask him, this is the second time I ask this young fellow this question. Mind games with E equals mc squared. You'll notice that the little m, it's a little m in E equals mc squared. And the reason we have fission energy, nuclear energy, is because of this equation right here. So let's imagine that one of these cups, can you hand me a cup there? Does it have something in it? Water. Okay, there's a cup. Okay, we'll take a picture of this cup. Ceramic cup, okay? We'll take it, we'll throw it on the floor, break it, pick up all the pieces. It weighed we weighed it first, okay? It weighed 1 pound. Threw it on the floor, broke it, picked up all the pieces and put them back on the scale. Young fellow, can you tell me how much it weighs now?
The same.
Exactly. Wow. Yeah, very good. Last time, the answer was half a pound. How we came up with that, I have no idea. But could be parental sarcasm. Now, let's make this cup out of wood now, okay, and let's burn it. Okay, it weighed 1 pound. Now it's going to be not a mechanical breaking apart, a breaking of that cup, but a chemical reaction. We're going to burn it. Okay, we're going to collect all the stuff. How much do you think it weighs now? Any ideas? It will be the same. This is conservation of mass. Okay. Well, if you could do that, the fact is all the molecules that you collect.
Catch all the molecules.
Well, you have to create a real clean environment in a small little location, and you could. Okay, let's say you could do that and measure the mass. Then it would actually be the same. But now let's take this cup and let's make it out of uranium, enriched uranium, bomb-grade uranium. Okay? We're going to shoot a neutron into it. Maybe a neutron from some material out here like californium that emits neutrons naturally. Just put it right next to it. It'll be fine. You can hold it. No radiation until that neutron hits it. It'll blow up. Okay, now we're going to collect all the stuff that blew up. Okay, let's say you could do that. Okay, put it on the scale. What do you think happened now?
I mean, what you're trying to get at, I'd say it weighs the same. But, we're talking about bomb-grade uranium. I really don't know.
Okay, well, the fact is, the energy, the huge amount of energy that when that exploded,
it uses a lot of energy.
The energy from the nucleus, the fission of the nucleus, caused this a little bit of matter to disappear, to actually disappear. So this thing is actually going to weigh less now, a little bit less, times.
Burn some of its mass.
to create energy. Before this, we never knew that energy, then this is where E equals mc squared comes in. The energy that's the large E, huge amount of energy. The small m is a little tiny bit of mass that disappears from that thing, disappears from the universe. The mass is no longer there. The matter is not there. It disappears. Okay, times 186,000 miles per second squared. So it's a huge amount of energy that's released for a little bit of matter. Okay? Thank you for participating. That's the conclusion.